Hopefully it's got room on it. We'll find out.
So that line basically stood for and.
That line means given.
Given. Okay.
I like it. That's just a quick way for us to say given. The book uses the same symbol, thank God. I don't know if you noticed yesterday I was all happy when I looked in the book because they used that symbol. That's the symbol for given. I like it. So now look at the formula. So if I wanted to calculate king, given, club using the formula, what's the probability of king and club? 1 out of 52, right? What's the probability of club? That's what's going to go on the bottom, right? What's the probability of a club? How many clubs are there? 13 out of 52. What happens to the out of 52 piece? Cancels. Right? It's the same on the top and bottom. I can cancel. I can multiply top and bottom of 52, so those go away. And I end up with 1 out of 13, which is, thank God, the same answer we got earlier. So the math does eventually get the number, but when I can just count stuff, I don't even use the formula. I just count. I think I've told you that already a few times. The formulas sometimes get in your way if you can just count what's going on. You need the formulas if you can't. They just give you numbers. Okay. So, let's take this away. We've got this formula figured out now. So the last formula we need to figure out is and. We don't have a formula for and yet. Math says, yeah, you do. Because I have an and up here, right? Here's the little bit of algebra. How do you solve for this? How do you solve for the top? So if I know that probability of A and B divided by probability of B equals probability of A given B. How do I solve for the top?
Multiply this by
Multiply that up, right? I don't want that here. If I want to get this by itself, don't I multiply by this to get rid of it? I love the way you guys work. How do you solve this equation? How do you solve that equation? Okay, everybody in the room go, ah. Ah. There are people in the room. Holy shit. Okay. Multiply by 3, right? So how do I solve for the top? If I don't want the bottom, I multiply by it. Right? So if I multiply both sides by this, let me write this the other way around. I get those cancel. So your probability A and B equals probability of B times probability of A given B. Right, now just wait for me. Just hold on for me. This is pure math business. I'm going to take this back into concrete stuff you can actually visualize, right? Or is basically add. And is basically multiply. Why does that fall into what I was saying about evil bouncer and nice bouncer? Because what happens when you multiply numbers that are less than 1? This is an interesting math question. Normally when you multiply numbers, they get bigger. What's 2 times 7? 14. That's bigger than both of them. But that's not always true. What is, for example, 0.9 times 0.8? What's 9 times 8? 72. And then you have to move the decimal back once, twice. 0.72. That is smaller than either of these, right? I'm just going to start some cheers. You guys, you got to let me know if it's not making any sense, and you also must let me know if it is making sense. I think you all maybe exist in the middle somewhere. I don't know. Do you understand what I'm trying to say? All right, 1 times 1 is 1. Anything bigger than 1, when you multiply it, it gets bigger. Anything less than 1, when you multiply it, it gets smaller. Because it's sort of, what does 0.9 kind of mean? 90%. So 90% of this is, of course, going to be less than that. It's going to get smaller. So and being based on multiplication makes sense. It's going to make it smaller. Less and less and less people can get in my club because you got to be rich and look good looking and have a nice car. And know Joe, the bartender. Hey, Joe. Hey. Or is addition. It makes everything bigger. You got to be rich or have a nice car or be good looking, or know Joe. And I'm like, thank God I know Joe. He lost me the other 3, but I'm like, hey Joe, hey, let him in. All right, yeah. All right. All right, so let's get to the concrete part of this. Okay. So I have I guess a morbid example, and then I have a silly example. So let me start with this serious kind of morbid example. So when I was a little kid, I lived in Florida. We used to go out and watch the space shuttle take off. Right, we could see it take off. It was awesome. The one time we didn't go out is when it blew up the first time, and I hate the fact that I have to say the first time. Back in '86, right? I was sitting in English class when I heard about it, and maybe that's why I don't like English as much as math. I was associated. I just had a breakthrough, and I started crying because I was a big geek, you know. But I don't know if you know why it blew up. It was because of these things called O-rings. So, for example, real quick, if you live in a really bad neighborhood, how many locks are you going to have on your door? Just one? Probably several. Why are you going to have several? Because you want to decrease the chances that somebody breaks in. If you got one lock, maybe they can crack that. If you got 5 locks, it's going to at least take them a while, and then you can hear it, and then you can call somebody. And then when the cops decide to show up, maybe you got the last one. Oh, shit. All right. So you're like, please do. So these O-rings were on the fuel line, and what they did was they made sure the fuel only went one direction. And it was icy that morning, so they actually didn't work correctly. The fuel went the wrong way, and boom, right? So let's say that the probability that any O-ring fails is, let's just say it's 1%. Hopefully it's actually less than that, but we'll just say it's 1% to make the math a little bit easier to work with. Do you really have to understand about space shuttle aerodynamics? No, you don't. There's just a 1% chance this thing will fail. You can think about it like a lock on your door. It's a 1% chance somebody's going to break into the lock. And so what's the chances this one breaks? 1%. It's another O-ring. It's got a 1% chance, made by the same people. I like it. So if I added these two to see what the total chances were, the chance that it fails grows. That didn't make any damn sense. I put more locks in the door, and the guy's like, thank you for that. No. It should get harder. The chance should go down. And sure enough, what percent of the time will this one fail? 1%. What percent of those times will this one also fail? 1%. And of course, what does of mean with percentages and fractions? Of means multiply. So if you multiply 0.01 times 0.01, what do you get? 0.0001, which is 1 out of tens, hundreds, thousands, 10,000. So now they went from a 1 out of 100 chance, that's what 1% is, right? To a 1 out of 10,000 chance. So if they put one more O-ring in there, that's looking pretty good. So every time you add another lock on the door, it's doing that. You're multiplying by... So if this lock has a 2% chance of somebody breaking in, and this lock has a 1% chance of breaking in, 2% times 1%, you've just made it even less likely somebody's going to break in. That's the idea of contingency plans or backup systems. I like it. All right. So that's kind of explaining at least a part of why it makes sense that and would be multiplied. This would be the probability that this one fails and this one fails, right? I like it. Now here's the silly example. This topic didn't used to be as controversial, but it's nothing major. I want to join a fraternity, right? I remember one time I said sorority by mistake, and they was like, sure you did. I want to join a fraternity. And they're going to put me through this hazing. Nothing crazy, nobody could die. It's just I got to walk down this hallway, and every third step I take, somebody's slap me here. And every fifth step I take, they're going to slap me here, right? So how often will I have this happen? Does everybody understand? How often will somebody actually hit me on both cheeks? Every third step, bam. Every fifth step, bam. Somewhere down the line, bam. Right? I'm kind of hoping these aren't big dudes or something. My jaw's going to have some trouble. You guys, come on. Think about it. Every third step, bam. Every fifth step, bam. How often will bam happen?
15?
15, every 15th step, right? Every multiple of 3, bam. Every multiple of 5, bam. So every 15th step, bam. What's 1/3 times 1/5? 1/15. 1/3 at a time, 1/5 at a time. So what's probably I get this and this? 1/3 times 1/5. I like it. So there's two kind of separate little examples about why and being multiplication makes sense. Okay. So let me get a little deeper into why this part is the given part. Yes, ma'am.
This so sounds stupid, but you said every third step, and then it went to every fifth step, and then 15, which I understand, like 3 times 5 is 15, but wouldn't it have been like 3 and then 9 and then...
Well, every third step I get hit on this cheek. So on the 6th step, I get hit on this cheek. On the 9th step, this cheek. On the 15th step, they match. On the 10th step, it's just this cheek. I like it. Cool. I like it. I'm so happy. I thought you guys were going to say, no, Jeff, we'll line up, and can you walk down the middle of us? It's too late now. I'm not going to do it. You could have said that. Like, all right, here we go. And you just take your frustration out. Come here, math boy. Bam! I'm step number 7, 6. Bam! Step number 8 just did it. No, that's not right. Start over. Oh, shit. All right.
How many steps did you have to take?
I don't know, man. Right now, 0. But I don't. None for right now. So this involves multiple steps. So I can't just pick. Like for example, if I want to go back to. Let me do this in case anybody has a lot of trouble with cards. Here's the classic probability setup, right? I kind of try to avoid this, but this is going to make it nice to make numbers really quickly. In a bag, I have 4 red poker chips. Well, yeah, say it like that, Jeff. It's really boring. 6 green poker chips and 8 blue poker chips. Is everybody cool with that? This is your classic probability problem. I'm going to reach in. If I only pick one chip, what's the probability that it's red? Make sure everybody's on board with me with the idea. 1? It can't be 1. That's a 100% chance. That means I'm only going to ever get red.
It'd be nice to see now.
4 out of 18. Alright, there's 18 chips. So how many things could happen? How many things could come out of there? 18 different things. And how many things match what I'm looking for? 4. So probability is always the number that matches what I'm looking for divided by the total number that could happen. Always. That's the basic idea of probability. Alright, so now what if I pick 2 chips? Get out of there. Two chips, different chips. So I pick a chip and I feed it to my little brother, like I used to do in the old days. I have 2 little brothers, so I can feed them both stuff. It's great. Pick 2 chips. What's the probability that I get a red and then a blue? So yeah, the probably get a red first off. Careful now. How did you get 12? You added, right? But what would addition be related to? Or. This is restrictive. It's got to be definitely a red first and then a blue second. Right? And it's 2 choices that I'm doing. So the probability that the first chip I pick is red is what? We already put it down. 4 to 18. Times and. I feed that one to my little brother. Yum, yum, yum. Go. Or I guess he just gulps it. I don't think his teeth are that strong. Yeah, careful now. What just happened? I fed a chip to my little brother. So when I go to reach in for the next pick, how many chips are in my bag? 17. 1 less freaking chip. Right? So it's going to be how many are blue? 8 are blue. Out of how many total chips now?
17.
So did this probability change from what it was normally? What was the probability of blue normally? 8 out of 18. Is it different now? Given that I picked a red first, what's the probability that I get a blue second? So this really is probability of red, because that's the probability of red, times the probability of blue, given that I got a red, which is exactly the formula that I had up earlier. So the second probability might change if the first thing that happens changes the situation. So now I could pick like 5 chips and just keep doing the same thing, right? Multiply, multiply. So what if I pick 3 chips? What's the probability that I get? Let me see if you guys can handle it. A blue, and then a green, and then another blue. So blue, green, blue. A blue, and then a green, and then another blue. So this feels like the fundamental counting principle, because how many spots am I going to have? 3. I got 3, not choices really, but 3 selections I'm making. What's the probability of the first selection? Yeah, 8 out of 18. So what changed now? How many chips do I have now?
17.
17. How many are green? 6. Now how many chips do I have?
7 of 16.
Careful. There's 16 chips, and I like it. How many are blue? 7, because I picked a blue one, didn't I? I love it. So sometimes the top will change if you picked one of them. You see, there's nothing major here. There's no huge computation, really. It's just that, do you understand why it would be multiplication for and? And I gave you a couple situations. One was serious and one was nowhere near. So the multiplication makes sense. And then each time you do something, it's going to change the probabilities that come after it. I picked a blue, so there should be 1 less blue down the road. Why is there all 6 green left? Because I didn't pick a green. They're all still in there. And then whatever you get when you multiply that out, I didn't even multiply those out, but what do you guys get when you multiply that out? 1/2, 1/3, 1/6, 7 over 100. So it's roughly 0.06 something. Is anybody doing that, or are you just waiting for me to make something up? You're just waiting for me to make something up, and you're like, that sounds good. You're a math boy. Go with that. My brain is not as good as a calculator. It gets close. Did I get close? Do I have to pull out my own calculator? How dare you make me do something?
Do you times the top and the bottom? Is that it?
So you ready? You can either do, put in your calculator, you can say 8 divided by 18 times 6 divided by 17 times 7 divided by 16. Or you could do 8 times 6 times 7 divided by 18, divided by 17, divided by 16. And that's the part that doesn't make much sense to people, but aren't these all freaking dividing? They're not multiplying. They're dividing into what the answer is going to be. But it's probably just best to put 8 divided by 18 times 6 divided by 17. Hey, what do you get? 0.069, really? Right?
Yeah.
That's pretty close. I like that. My brain is working semi-well. All right. It's my one skill, and I try to show off for you, but hold on. All right. So, yes, this one.
Sometimes all the tops across and the bottoms all across and then divided them and then still came up with that number.
Good. Beautiful.
That's okay.
That's sort of like doing your checkbook and you add all the positives and you add all the negatives and then you subtract those.
Okay.
Same idea.
Okay.
I like it. Okay, so everybody good with that? So I'm going to give you a situation just like it. If you have the practice test near you, if you look at number 7, sounds a lot like what I'm talking about. The only thing, there's a situation that's actually easier than this, that I'm going to talk about now. It's sort of like learning how to drive manual, and then let's do automatic. Well, that's easy. If I wanted to do all this, let's say I do like number 3 again, but I say I pick 3 chips, but every time I pick a chip, I look at it, and then I drop it back in. I pick another chip, I look at it, and I drop it back in. My little brother's over there saying, I'm hungry. He's developed a taste for poker chips. I'm like, oh shit. A little poker chip monster I've created. So if I want to do what's called with replacement, if I do this with replacement, this is without replacement. I pick 3 different chips. So I throw the first chip away, throw the second chip away. This is putting them back in. So the only difference is it's actually easier. Probably the first one's blue is 8 out of 18. I then put that chip back in. So what's probably get a green chip now? 6 out of 18. I mean, the probabilities don't change now because I'm putting it, I'm resetting it every time. 6 out of 18. And probably blue is still 8 out of 18. And then whatever the hell that is. So when I say with replacement, that's nice. Nothing changes. When I say without replacement, now that's going to affect everything else that comes after it. Cool. So you can see on number 7, I got a with replacement part and a without replacement part. So that's how those work. Cool. Okay. So a couple of last little definition things, and then I'm going to let us out of here early. Because it looks like you guys need it. Or do you guys act like this just because you know that makes me let you out early? Is that what it is? You know, like everybody put, you can go home. Yes. Okay, maybe that's a good idea. That works. So everybody got what they want from up here? More than you ever wanted? Okay. So 2 little definition kind of things. Let me put up here in the corner of these. I'm going to need these here in a minute. What was the joke? Oh yeah. Alright, so there's 2 definition type things, situations. 1. If A and B are what's known as mutually exclusive. So let's break this word down, this phrase. When I say the word exclusive, what comes to mind? Sorry? Exclusive. Yeah, if I say I'm going to this exclusive club, that means that I might not be allowed in, you know, right? So something exclusive, it excludes certain people. Right? If you don't have money, if you don't have enough status, if you don't, whatever. Mutual means, exclusive means that they exclude each other. I'm like, you don't want me, I don't want you, right? That whole thing. So if A and B are mutually exclusive, that means that nothing in A is also in B and vice versa. So for example, if I picked up one animal, could I have just picked up a turtle and a hamster? Could this animal be a turtle hamster or a hamtel or a turster? No, right? Is everybody cool with that? I used to say cat and dog, and then there was cat dog or something. Anyone ever seen that cartoon? It's a cat and a dog, and I'm not going to talk about the biology of it because it just concerns me. But oh, think about it, like, where does certain things happen? Okay, too. So what does that mean then? Like if I have a room full of turtles and hamsters, right? And I walk in, and I'm being careful, shuffling, not lifting my feet up so I don't step on anybody. And I reach down, let's say there's 5 turtles and 5 hamsters in this room. And I reach down and pick it up. What's the probability I just picked up a turtle? 5 and 5.
10. 1 10. Well, 1 and 5.
What percentage of the animals in there are turtles? 50%, right? All right, let's try this again. There's 5 hamsters, 5 turtles. I'm blindfolded. I pick up an animal. How many turtles were there again? 5. How many animals?
10.
So it's a probability it's a turtle I'm holding?
5
out of 10. 5 chances it's a turtle. Divided by 10 things it could have been. So 50%, right? Now I take my blindfold off and it's a hamster. What's the probability it's a turtle now? I look at it, it's a hamster. What's the probability it's a turtle? 0, right? It's like, haha, I got a mask. No, stop. So what I'm trying to say is, if A and B are mutually exclusive, that means the probability that A and B has to be, can it be a turtle and a hamster? No. So what's this probability have to be? What's the probability have to be if it can't happen? 0. So mutually exclusive means this. That's what mutually exclusive means. Cool. So then if that's 0, then this would be like subtracting nothing. So for example, if I said, what's the probability I pick a jack and an 8 out of a deck of cards? If I take one card, it's probably a jack and an 8. 0. All right. So what's probably I get a jack or an 8? How many jacks are there? 4. How many 8s are there? 4. How many cards are both? 0 cards are both jack and 8. If you have cards that are both, I'm not playing any games with you. Oh, I got a full house now. Screw you. Minus 0, it's not even there, right? I don't have to subtract anything because there's nothing that I counted twice. Out of course, 52, blah, blah, blah. Okay. Alright, so that's the idea of mutually exclusive. It's kind of a nice, it kind of makes complete sense. They mutually exclude each other, so it's probably, it can be both of them. None. 0 chance. Because they mutually exclude each other. So last thing. Independent. If the probability of A given B is the same as what the probability of A used to be. So if I tell you something happened and the probability of A doesn't change, so A didn't give a shit that B happened. Do you guys see that? B happens. Did A care? No. Well, I would call this independent events, which makes complete sense, right? And I've talked about this already. I just wanted to remind you guys. So if A, probability of A given B is the same as probability of A, then they're independent. And now look, how would this change then? If they're independent, what's the probability of B given A equal to? See if you guys can turn that around. Given A, does B care if they're independent? No, so that's the same thing as probability of B. Then I am just multiplying those directly. I don't have to change anything. And that was when I did with replacement, nothing changed. Because then they're independent. If I don't throw a card away, the second card doesn't care what happened in the first go. Anything could happen again. I didn't decrease any possibilities. All right. That's plenty. So don't forget, I'll have the answer key for this practice test actually on Tuesday. Our test is on Wednesday.